Since we've done a lot of problem solving and discussions about conduction through materials like slabs, hollow cylinders, and hollow spheres, it's time to move on with a more practical application of this conduction, which is in series and parallel orientation of materials. Before we start, we need to go back to the original equations that we've had before, which is the rate of transfer process, this one, what is written here, the rate of transfer process equals driving force over resistance, so that we can derive the equation for our conduction in series and parallel. In this case, this is the general equation for conduction through slab, which is just one slab and with a thickness delta x. So if you wanted to try to find the resistance here, what we need to do is to equate this equation into the rate of transfer process, which in this case is our Q. So this is equal to the driving force divided by the resistance. As what we have mentioned before, in a transfer, the driving force is always the temperature. In this case, T2 minus T1 is our driving force. Going back, since we've already cancelled T2 minus T1 being the driving force, we just need to find the resistance, and this will play a very vital role in our generation of the equation for our series and parallel conduction. In this case, what we're left with us is simply A, which is the area, multiplied with our thermal conductivity, divided by the thickness of that slab. This is equal to 1 over the resistance, or the reciprocal of the resistance. So in this case, if I wanted to ask you what is the resistance, or simply the resistance R, so what it will give you is the reciprocal of this equation here. So what we'll get is delta x divided by the area times our thermal conductivity. Since we've already determined our resistance, now it's time to derive the equation for our conduction in series. When we say conduction in series, we are referring to conduction in which the slabs, or let's say any material in arrangement, they are in adjacent with each other. In this case, these 1, 2, 3 slabs are adjacent with each other. So we call that we call those material in series, okay? And of course, if they are separated and there's no contact in between them, then it is in parallel. And we'll be focusing more on the series because parallel orientations are much less common, and in general you're just adding the conduction of heat with each of the solid material. So what is evident in any conduction in series is that the total heat generated is equal to the heat that will be experienced by one slab, which is also equal to the heat that will be experienced by the second slab, then the third, and of course to any additional slab that you have. And that is the same for the conduction through a sphere and for a cylinder as well. So for as long as there are adjacent material with the first one, then it will just experience the same heat loss or heat of conduction. So if that is true, then let's just try to have derive one equation for our, let's say, 1. We call this delta x1 since we're talking about 1. And then let's just try to have some t1 here, and then this one is t4. Or we can just say t3. Oh no, it should be t4. Because it simply means that we have almost 4 temperature profiles here. The first one is the T1, which is the inside temperature, and then at the interface of 1 and 2, so we can have there T2 right here, and then T3 at the interface of 2 and 3, and at the outside or the environment temperature would be T4. So if I wanted to find the value of our Q1, which is the heat of conduction experienced by the slab 1, we could just simply say that Q1 is equal to the change in the temperature, which is simply T2 minus T1 divided by this should be multiplied with our thermal conductivity and then the area, and then this one should be divided by the change in the dimension, or simply the thickness of that slab. And of course we should add some 1 here, and K1. Remember, our thermal conductivity would vary because the material is usually different from each other. And if I wanted to find Q2, that is also K2 multiplied with our T3 minus T2 area sub 2 and then delta x2. And by the way, if you ask me where's the negative here, we can actually add the negative here, but the thing is, if we are considering T2 minus T1 being T2 the lower temperature, then then the negative has already been distributed. But for the sake of these equations, let's just use something like T2 is less than T1. So that, yeah, I should add some negative for that. Okay. So, because if T2 is less than T1, then this will be negative. Okay. So with that, let's continue for Q3. So we get negative K sub 3 multiplied with T4 minus T3, then area sub 3 delta x 3. Okay. And in this figure, though it looks like they have the same thickness, most problems do not have the same thickness. So let's just not focus our thinking about this problem in which the thickness have the same values. So if this is true, then we could just simply equate all of these differences or the equations here with each other, and then this one is Q2. So we get here T3 minus T2 area sub 2 delta x. So these are the relationship that we could get, but when we try to add all these temperature differences, what we will get is simply delta T total, which is equal to T2 minus T1 plus T3 minus T2 plus T4 minus T3. And with that, we can just cancel out all of these, and then we're left with our delta T, which is the temperature gradient from our inner to the outer, which is equal to T4 minus T1. And remember, delta T here can be this T2 minus T1 can be substituted with each of the equations that are involved in this manner. In that case, we're left with what we call the Q, which is equal to the temperature gradient minus T1, then divided by our total resistance. And our total resistance is simply equal to each resistance that we have obtained. In this case, we only have 3, so let's just have some there. And remember, if T1 is higher than T4, we could always add some negative here. Okay? And if we do have some R1, R2, R3, then we can simply write here the expression of each resistances that we've already solved. In this case, our Q, or the final heat rate that we can get, is simply T1 minus T4, assuming that 1 is higher, divided by R sub 1 is simply the resistance of 1. And in this case, we do have this kind of equation, which is 1 over R. And this is the final equation for every resistance that we can get. So for slabs, what we get here is that R1 is simply equal to the change or the thickness of 1 divided by area multiplied with its thermal conductivity. And for R2, what we get is thickness, then divided by the area 2, and then K, or thermal conductivity 2. Then plus delta X3, then area 3 multiplied with thermal conductivity. And what's good about slabs is that they are usually they have the same area for each face. So in that case, if our area 1 is equal to area 2, and that is also equal to area 3, then what we'll get is simply we can just substitute these in terms of A, and then you can simply factor it out to our equation. So we're left with Q is equal to T1 minus T4 divided by, of course, that is if the problem says that they have the same area, but if not, then don't do it. So this is delta X sub 1 A K sub 1 plus delta X sub 2 A So in this case, I can just simply factor out 1 over A, and then that 1 over A will be placed at the numerator. So that is area multiplied with T1. So that is Q is equal to area multiplied with T1 minus T4, then divided by each resistances. Okay, so this is our final equation for conduction through slabs. In this case, to be able to understand this in a clearer way, let's try to solve a problem that involves such kind of equation. Now let's try solving this problem. What we have here is a conduction in series, and I wanted you to pause the video so that you can understand the problem, and just go back after you've read the problem. So I hope you've understood the problem, and first thing that we need to do here is just to draw this composition so that we can generally think of a solution about this. Let's try to draw a composite wall, and then the first one is 2.5 cm copper plate, of course, and this is not the scale. The next one is a layer of asbestos, and the last one, which is the thickest of all, is the fiberglass. Now this is composed of 3 layers, and what is given to us is the change in temperature, or what we call the change in temperature, or the temperature gradient, which is equal to 560 degrees Celsius. And remember, 560 degrees Celsius is not the average temperature, but it is the difference between the two surface temperature, of course, from the inside to the outside temperature of our composite material. And the next question will be, to what temperature would be evaluating our thermal conductivity so that we can get all the values for our K? And to answer that question, it is actually difficult to find that one because we're only given with 2 temperatures, and it's the difference. So we can't do something about it. And the first thing that we did was to generate a linear equation. But for cases like this, for series conduction, it will be very difficult for us to generate linear equations for each of the for the 2 materials that are left. So what we'll be doing here is just use some practical knowledge about our heat transfer. Now, the first one that we need to understand is how is this material being constructed. Of course, it's written here that it is copper, asbestos, and fiberglass, but are we sure really that the composition is just adjacent to each other? Wouldn't it be that the copper plate should be at the middle side or whatever? So in that case, let's try to analyze this one. This is a composite wall, and probably this could be a wall that is constructed so that we can enclose a certain fluid. In those cases, for example, the fluid is really at high temperature because remember this temperature difference is really high. So in that enclosure, it could probably mean that the copper plate is what is in contact with the fluid. And then of course, if you wanted to insulate it, the next one would be the asbestos, and finally the fiberglass, which is exposed to the environment. So it practically makes sense if we do something like this. And then if you wanted to try like asbestos being at the first or the layer that is exposed to the fluid, then it would have been a disaster because asbestos is actually a harmful material, so it shouldn't be exposed to any fluid of any kind. So in this case, this should have been the best composition of our wall. And either way, the answer would just be the same. It's just that the temperature gradient would be somewhat different if we have arranged all this material in a different manner. So if you would like to take a look at the temperature gradient, then this is probably the temperature gradient because we would assume that T1 is the highest temperature and T4 is the lowest, which is the outside temperature. So the next one is that we've already derived the equation for our conduction through series, and in this case, the area is the heat flow is asked in which it is divided or per unit area. So we're assuming that all the slabs have the same area. So with that, we're just left with the temperature gradient, which is equal to T1 minus T4, and we're already given by that value, which is 560 degrees Celsius. Then this will be divided by all the resistances which is offered by each material. That is delta X1 divided by K1 plus our delta X sub 2 divided by K sub 2, and then the last one is our third material. So this is our formula, and this is pretty easy if we just have this thermal conductivity. What we're given is the thermal conductivity of fiberglass, and that is K sub 3. So we only need to find K sub 1 and K sub 2. In that case, K sub 1, which is equal to the thermal conductivity of copper or copper plate, so since we've given with a table in Paris Handbook, and you also have, I think, a table for 9th edition, but this 9th edition is actually really very difficult to understand since I think this is not yet the final release of the PDF. So I think I won't be using this for now because I do have some bookmarks here, but when I click it, it doesn't lead me to the correct. I mean, sometimes it does, but most of the time it doesn't. So let's just use it some other time. Now let's go back with our 8th edition, and we need to find copper. We've used this table before. This is the thermal conductivities of building and insulation materials. But since copper is not an insulating material but a metal, so we'll be taking this table 2-327, which is the thermal conductivity for metals. And in this case, we do have copper, but the what's difficult here is that we're given with a lot of thermal conductivities, and we couldn't actually pick which one is right here, since we're already given with only the difference in temperature. Now, what we'll be using is just some practical application of what we have in engineering. Okay, So remember, if you're given with a lot of data which have a lot of differences, I mean, let's say for example this one, 19,000 and 10,700, that is in almost less 9,000 difference. And that's just an increment of the change of temperature at least 10. And this is a very low temperature. So remember, your copper and having that kind of temperature difference, which is 5-6 degrees Celsius, we can simply tell that the problem has a high temperature. And of course, the environment, if we would just think that the environment is just around 25 degrees Celsius, then it is probably safe to assume that the temperature in Kelvin is around something like 600 or 500. And in that case, it is, it could have been around 600 or 800, but it is safest to take the value in which we would have a minimal difference in each two values. So what I mean by that is just we take a look at each values here, and from 300 to 1200, we're only having some values ranging from 342 to 398. And with all of these values, as we can see here, this value 392 and 388 do have only the minimal difference, which is just 4 units. Well, if we take this 388 and 383, we have 5, but the only difference is just 1 unit. So in this case, if we do have this 392 and 388, then we could just simply say that the our value of copper thermal conductivity should be around here. But if we just think about the difference, which is 560, and assuming that the environment or the the temperature outside is around, let's say, just 20 degrees or 25 degrees, then probably the best option would be around here. If you take the average temperature around 500 to 600. And yeah, so the explanation to that is that we just assume that T4 is around that temperature, although we couldn't actually tell for sure. But that's the best way that we can assume the value of our T4. And with the change, we can just probably the temperature would be 500 to 600. And with that, since we do not know exactly what is the temperature, I'm not referring to 560. I'm just telling that T1 should be around that temperature. So in that case, we can just simply take the average of this 388 and 383. So what we'll get is 385.5. So we'll be using that value for our copper. And of course, it makes perfect sense that this is very high compared to our fiberglass, since copper is a thermal conductor. Now we proceed with K2, which is our asbestos. Before, we've obtained asbestos using some kind of linear equation derived from our table, but now, since it will be very difficult for us to integrate those kind of equations, then we would simply assume a value of our asbestos. And the best way we can assume that is just to check on this temperature first. So asbestos is around the middle of our material. So assuming that it's at the middle, we could just simply think that it should be, of course, greater than 0. But could it be less than 100 or less than 200? So the only option that we could just say is that it should be around less than 500 degrees Celsius. So in this case, it is safer to assume that our asbestos is just around here. Of course, it's greater than 0, but I'm not saying that it's less than 100. I'm not sure of that, but we can just simply take on this values because it is a more practical way of finding a value which is less than 100, I think. But what if in your solution you just chose this one? I still think that it will be okay for as long as the values of the asbestos or the thermal conductivity you have obtained is around somewhere here from 0.087 to 0.120. I mean greater than 0.087. So with that, let's just take the average of that too. So I will be getting around 0.099. So the K of our asbestos is 0.099. And I believe that the unit in that table is in English, so we still need to convert this in SI unit. So now we can simply solve for our Q over A. And in this case, let's try solving it. Q over A is equal to the change in temperature, which is 560 degrees Celsius, divided by, so what we have here is, first is delta X sub 1, which is the copper plate, and copper plate is 2.5 cm. So we need to convert this to meters. So I'll be dividing it with 100 and then divided by our thermal conductivity, which is 385.5. So we need to make a consistent units here. So usually we need an MKS unit, so meter, kilogram, seconds. So, and SI, since most of our given here are already in SI units. So we need to take the second resistance, which is delta X sub 2, so that is 3.2 centimeters, and we also need to convert this to meter. So that is the essence of 1 over 100, and then divided by, this is divided by the thermal conductivity of asbestos, which is in terms of in English. So I think I'll have a separate computation here so that I can write here the converted value for K. So with this, let's try to convert this in our 3 degrees Fahrenheit. So let's convert this one first. So if we have something like 1 British thermal unit, what we have here is around 252.16 calories. And then 1 hour, since this watt is joule per second, so we need to convert this R into seconds, and what we have here is 3,600 seconds. And then feet, so since we need meters, so what we get here is around 3.28 feet is simply 1 meter. And then degrees Fahrenheit, if we wanted to convert degrees Fahrenheit, so, and this is referring to a change, so that is 1.8. For every 1.8 degrees Fahrenheit change, there's actually 1 degree Celsius change. So in this case, we will be having and then calories, we also need to convert calories in terms of joules. So what we have is that 1 calorie is 4.184 joules. So what we get is 1 calorie and then 4.184 joules. So cancel this out, and then hours, feet, degrees Fahrenheit, and of course we're left with joule per second, meter, degrees Celsius, which is watt per million Kelvin. So I'll be computing this. So what we will get is simply equal to 0.1713 watt per meter Kelvin. And magic trick that I would always like to call in heat transfers, that if you are given with thermal conductivity in terms of English units, you can just simply multiply this with 1.730735, and then what you will get is it should be this one. Okay, so if you do that, then hopefully we could just get the same answer. So yeah, we also get 0.1713. So that is the shortcut, most shortcut way of finding the thermal conductivity in terms of SI units. So with that, we're left with 0.01713, and then add some delta X here, which is around 5 centimeters. So you need to have some conversion factors for meters, and then 0.04, I believe. So yeah, and then with that, let's just continue this here. So we're left with Q over A. So the unit would be in watts per meter squared. And the answer for that is, let me just calculate it first. You can also do the same while calculating this. Probably I'll be fast forwarding this video. So the answer in watts per meter squared is 389.7356 watts per meter squared. So this is our heat flux. So that is how we solve for the thermal conductivities. That is, the heat of conduction, that is, of course, for materials that are in series. It doesn't only exist in this kind of material, but it also exists in materials like cylinders. To be able to understand the equation better, let's just solve this problem, and probably we could just, get a good understanding of the situation in our conduction in series. And by the way, you might want to pause the video and then come back here so that you can just easily grasp the whole problem as I go on with the solving of this certain problem. So I hope you have read the problem and you have understood it clearly. Now, we start solving this by simply analyzing the problem, and the problem is a simple one. We just have this fluid temperature of 223 degrees Celsius on the inside, and the outside, which is 57 degrees Celsius, and there is a second fluid that flows outside. But technically, we don't have to deal much more about the fluid outside or the inside, since the effects of these are neglected. So in any case, it simplifies our computation. And if we are asked to find the heat loss by the tube per meter of length, we actually need to find Q over L. And from our equation, we have Q is equal to 2 pi, then multiplied with L, and then the change in temperature. In this case, if I have T1 here from the inside, and then from the outside, since I do have two resistances here, one that is given by the steel tube, and then the other one being given by this silicon carbide. With that, the expression should be T1 minus T3, and then that is divided by logarithmic difference of R2 and R1 divided by the thermal conductivity of the steel, and then added with another resistance given by R sub 3 over R sub 2, and the material is the silicon carbide. So this is our general equation, and we just need to plug in all the values that are given in our problem, and of course from the table if we need it, and just have to find the answer. And by the way, we could just simply divide both sides by L so that we can cancel L from this equation, from this relation. So in this case, I just need to find our R sub 2 first. So with that, our let's just write here our given, those that are already stated in the problem. So we have 46 watt per meter degrees Celsius, which is the thermal conductivity of the steel, and then an inside diameter, which is di, that is equal to 3 centimeters, and then a tube wall thickness of 2 mm. So with that, let's just have something like R sub 2 minus R sub 1, because if we're basing this on the figure, we can simply subtract R2 by R1, and then what we'll get is the thickness. So I'll just name thickness as T1, because that's the thickness 1. That is equal to 2 millimeters. And then, so fluid flows on the inside of the tube, and while the second flows across the outside of the tube. And then neglect the effects of convection. That's very important. So the inside fluid temperature is 223 degrees Celsius. So we can say that T1 is equal to 223 degrees Celsius. And then the outside, which is T3, that is equal to 57 degrees Celsius. And then we need to calculate this heat loss per length, or per meter length. And then the insulation is R sub 3 minus R sub 2, which is equivalent to the second thickness, that is 1.5 centimeter of silicon carbide. Technically, the second thickness is much thicker than this thickness 1. It's just that we somehow need to increase this, so that even though this is not a scale, we can just understand and take a good grasp of what's happening on our problem. Okay, beautiful. So with that, let's proceed with computation. But before anything else, since we will be using R sub 2 here, then we need to find R sub 2 and R sub 3 respectively. With that, remember, R sub 2 is actually equal to R sub 1 plus the thickness. So in this case, since R sub 1 is simply 1/2 of our inner diameter, that is 1.5 centimeter, and then we add some thickness, which is 2 mm, and that is simply divided by 10, because I have to convert it into meters. So what I will get here is actually 1.7 centimeters. So the next thing that we have to do is to find R sub 3. And R sub 3 is simply R sub 2 plus thickness sub 2. And with that, that is 1.7 centimeter plus the thickness 2, which is 1.5 centimeter. Adding these two, what we get is our R sub 3, which is equal to 3.2 centimeter. So you might want to use your calculator if you could. You're having suspicions with our answers, but of course, as engineering students, you should always be using your calculator, even if it's just adding numbers with decimals or fractions. Because we always have to say in engineering, the accuracy is always better than speed, because in the end, they're both they're equally relevant to solving problems. But the thing is, it is better to be accurate than fast, because you can be fast but you're not accurate, and that's a very unfortunate thing to happen in exams. Okay, so anyway, so we have R sub 1, R sub 2, R sub 3. We have the steel thermal conductivity, and now we just have to find the thermal conductivity or silicon carbide. So since this is not given, you might have an idea that this silicon carbide can be located at your Paris handbook. So I hope that it is included in the 9th edition, since remember, I've talked about this, and it is not located here. And I think it is not, because this is the thermal conductivities of insulating materials, and unfortunately, one of the most important tables has been removed from your 9th edition, and well, that's so sad. But let's just I will just be giving you some tables if I need it, and you can do your own interpolation for those tables that I will give during your quizzes or your exams. Anyway, since we already have the silicon carbide here, which is a break recrystallized, so that's what this problem is referring. So the question is, what temperature will we be evaluating our silicon carbide? Remember, we always have to consider the average temperature in order to find the thermal conductivity. Okay, And in this case, if I wanted to ask you at what temperature would that be, you don't have to say something like, okay, let's just take the average of this 223 and 57. If we do that, let's just take the average of those temperatures. So if I would take the average of that temperature, that is T1 plus T3, which is equal to 223 plus 57 divided by 2, and then the average temperature, while using those two, would be equal to, actually solving, so that is 140 degrees Celsius. So what I mean by this is that, well, it's true that we might as well want to take the average so that we will be able to find the thermal conductivity. But there are actually two cases that we might consider. First, that the exposure of this silicon carbide to the outside environment, which is at 57 degrees Celsius, would, of course, it would give a contribution to the thermal conductivity, since this is an insulating material. As the temperature increases, the thermal conductivity also increases. So in that case, it should be increasing if we will be considering 57 degrees Celsius. But of course, since this is a very thick one, and then as you can see in the figure, though this is not to scale, the contribution of the higher or the hotter region would be as if it's almost at the center of this particular steel pipe. So what I mean by this is that if we wanted to evaluate the thermal conductivity of our silicon carbide, then we should be using the average temperature, which is actually T3 and T2, and then just take the average. This is for our silicon carbide. So this should be the thing that should be done, because this is technically the average. But if we will consider this one, then this is 140 degrees Celsius, and we know that this is for T1 and T3. So if T1 is higher, of course, than T2, and then we will consider T3, then supposedly the average temperature should be lower than this average temperature that we've obtained from these two temperatures. So yeah, that's it. So I just wanted to tell you that you can use the average temperature for these two temperatures, but you can also use the last temperature, since this is exposed to the environment, and we don't actually know what particular area would the thermal conductivity lie on the larger contribution for this case. So in that case, we'll be solving for two solutions. We'll be solving for each of them using the average temperature for T1 and T3, and then the other one is just using our T3 here. So because we don't have any value for T2, and if we have, then it could have been a lot easier. So using our average temperature, which is 140, let me just use that to extrapolate here. I'll be using only the two values here, which is 600 and 800. So I'll be extrapolating, so you might as well want to extrapolate as well. And since as the temperature increases, it should be that the insulation should be decreasing. So our temperature using 140 degrees Celsius in English unit, our thermal conductivity, sorry. So that is equal to, so our thermal conductivity, so this is at 140, thermal conductivity is equal to 14.15, and of course the unit is in British thermal unit per hour, and then feet, and then degrees Fahrenheit. And then for our temperature that is at 57 degrees Celsius, what we have is 14.7725 British thermal unit per hour feet degrees Fahrenheit. So I've already solved for the conversion of this English unit to SI unit. So I will just be multiplying this with 1.730. Sorry. I would just be multiplying this with 1.730735 so that I can get the thermal conductivity in terms of SI units. So with that, I have 14.15 times. So that is equal to 24.49. That is in watt per meter Kelvin or degrees Celsius. And the other one would be, of course, it will be higher. That is, but it's not that really high. So we get 3 watt per meter Kelvin. So now we can just simply plug in the values for our equations here, and let's try solving for 140 and 57, and we might as well have an idea of what should have been the better choice for these two thermal conductivities. So we have Q. Let's try having some different color. That is Q over L equal to 2 pi multiplied with the change in temperature, which is 223, and then 57 divided by ln of r sub 2, which is equal to 1.7, and then the other one being 1.5. So remember, we don't have to convert this 1.7 and 1.5 into meters, simply because they're in ratio, and we are taking the logarithmic value of this ratio. So the thing is, even though you've converted these values into meters, you will still get the same answer. So just for the sake of having faster calculation, you don't have to convert it anymore. And then we proceed ln of the ratio of the areas divided by the thermal conductivity, which is already given here, and it is 46. So the first portion here of the resistance is for the steel, and then the next one would be for our silicon carbide. That is 3.2 divided by 1.7. So let's just try to take a look at 140 degrees Celsius. So I will be using this one first. That is 24.49. Okay, so I just forgot to write the units here. You might as well want to write it. I hope I can write it well here. Okay, so we cancel this out, so we're left with watts per meter. So the answer here, I'll be using my calculator, so might as well want to use it also so that you can follow through. And the answer should be, so the answer is 36,534.335 watts per meter. So the unit should satisfy our function here, or our expression, that is the heat rate divided by the length. So that is watt per meter. And remember, watt is joule per second. Now let's try using the same equation, and then we'll just be substituting the value at the latter part, which is 24.49. We'll be substituting that with let's try another color. We'll be substituting this value with 25.5673. So I hope you won't get confused with this writing, but with that, the answer would be equal to, so just put in your calculator and just write it. Okay, so we have 37,982.215. Okay, so the answer, if we chose the higher temperature, that is 36,000, and for the lower temperature, that is 37,000. So given this heat rate, we've already obtained the answer, the heat rate per meter. But what is the best answer for these two? Actually, these two answers are already correct, but what is the best answer if the problem asks you, for example, the problem asks you to solve for two cases, and then you wanted to choose from it, then what will be your basis of finding this answer, which is better? So what we'll do now is we will evaluate the changes in temperature. In this case, I'll be needing our T2 so that I can jump into conclusion which one is better here. Now, if T2 is a lot higher than this, let's say than 140, I mean a lot lower than 140, then the better choice would have been 57. But if it's close to 140, then the better choice would be 140. That's just a fairly simple analogy. Now with that, let's try solving for T2. And the only thing that we could do for T2 is that T2 is actually equal to T1 minus delta T1. Or we could just simply say that T2 is actually equal to our T3 plus delta T2. So those are the cases in which we can solve for T2, because delta T1 is equal to T1 minus T2. Okay, so in this case, T1 minus T1 minus T2 would be positive T2, and delta T2 is actually equal to T2 minus T3, and that would make perfect sense if you would add these two. Okay, so with that, using the equations that we have here, that the total heat is actually equal to our the heat contribution for each one, because they are adjacent with each other. So in this case, Qt is equal to Q1. We could just simply say that the change in temperature for the first one, or the steel, would be equal to the resistance offered by the steel multiplied with the whole change in temperature, then divided by the total resistance, that is R1 plus R2. So this is what we call the best assumption that we could give into the change in temperature, simply because the ratio of the resistance to the whole resistance, I mean R1 to the whole resistance, is, if you would multiply this to the total change temperature, then that is particularly the ratio and proportion which we will use in Qt is equal to Q1. So in this case, we can solve for delta T1. So remember, the first resistance is equal to the ln of 1.7 over 1.5, that is R sub 2 over R sub 1, divided by the steel's thermal conductivity, which is 46, and then this will be divided with the total resistance, that is ln of 1.7 over 1.5 over 46 again, and then added with the resistance offered by our silicon carbide, which we will be using the temperature at 140. Okay, so this is at 140 degrees Celsius. So what we get here is simply ln of 3.2 over 1.7, then divided by the value, which is 24.49. And of course, the change in temperature would be the total change in temperature, because it doesn't make sense if you would just use another value. So that is 223 minus 57. Okay, so in this case, if you solve for this, then that is our change in temperature for our first value. That is, now let's just solve for it. So the change in temperature is 15.8212 for temperature at 140 degrees Celsius. In this case, if you wanted to find T2, then T2 is equal to the first temperature, which is 223, then subtracted with 15.8212. Then therefore, T2 is equal to 207.1788. So that is our value for T2. Now, this 207.1788, is it like closer to 140? Is it closer to the average of T2 and then T3? Or is it closer than T3? So I think you already have the answer for that. Because if we wanted to like solve for the average using this T2, what we'll get here is 207.1788 and then added with 57, then divided by 2. The answer here would be equal to 132. Okay? And this answer is actually close enough to this value of 140. And therefore, with that, the correct answer that we will be reporting, or probably the best answer, would be this 36,534, knowing that it is evaluated at 140 degrees Celsius. So in this case, remember, I've told you before that even though this is at 140, we have to expect that the average temperature is lower than this 140, simply because this is the average temperature of T1 and T3. Imagine if T1 is at this point and then T3 is outside here, then if you would take the average of that values, then you would still consider somewhere at the middle of this arrangement. In that case, that is 140. But if you would simply take the value at the interface of T2 and T3 and then T3, then that simply means that it is somewhere farther here from the center, from of course the inner side of our equation, which is a lot closer than our 57 degrees Celsius, and that is the colder region. So with that, we've already evaluated the answer. If we're only asked with Q over L, your answer is actually still correct, or could have been just 1 point less than the most number of points that you will get. Since there's not really much big difference, since the values of K is actually a lot closer to each other. But since we're dealing with accuracy here, and of course we don't have to disregard all the losses that we could have in process design, so we have to consider what's best for each case, and this is the best one. With 140 degrees Celsius at K, the value of our Q over L is much, not that much less, but it is a better option than this one. Okay, so I hope this makes it clear for the cases where we have to just infer or just guess which temperature will be evaluating our thermal conductivity. Thermal conduction is actually a very easy topic. It's just that the given in the problem in which we need to find the values where we have to interpolate or generate our own equation and then apply some principles of physics and chemistry. Those are the things that make it more difficult. And when we analyze things, we have to consider all these real scenarios of these problems, and it is much more difficult for students since you're not that really exposed to the certain processes in the industries. But in the end, you will just I think just solving a lot of problems will deal with that problem. And you can always check your answers if you've obtained a really different answer for these two, but knowing that the values of thermal conductivity are just close with each other, then your answer might have been wrong or incorrect. So okay, remember this formula here is usually used in evaporators that we will be discussing on a later subject and a later discussions. But But of course, I have introduced this to you first so that you would not get confused when I'll be using this on our latter discussion about heat exchanger as well, and evaporators and crystallizers. So with that, that ends our conduction in series. Now let's move on with our conduction in parallel. But I don't think I will be giving another example. I just have to discuss it since conduction in parallel are just these are just problems that are made in a way that it is parallel, but technically it's just two bodies having some conduction at the same time. So in parallel, since remember in series, this like you remember your series circuits. When we talk about series, we're referring to this something like current. In series conduction, our Qt is equal to Q1, that is equal to Q2, that is equal to Q3. So this is the same until Qn. And this is like describing the current that is experienced by resistors in series. Okay? And of course, if that's the case, then how do you think the current that will be experienced by the total current that will be experienced by each resistor? So in this case, in parallel, we'll be describing our total heat, which is the sum of all the heat conduction that is experienced by all the material that is involved in that particular problem. Okay, so that's fairly simple. That's just our materials having the same conduction, having conductions simultaneously. So I won't be giving another problem solving, but of course you still have to study something like this, and that's fairly simple. If I have something like two slabs here, and then if I wanted to ask you what is the total heat that is experienced by, what is the total heat of conduction, just that's just the question. So you will be having simply Qt. Let's say this is 1 and this is 2, so that is simply Q1 plus Q2. For example, I have area 1 here and then area 2 here. This one is delta x1, this one is delta x2. Of course, the temperature that will be starting here is just the surrounding, let's say inside. So I have T1 here, and then at the other side would be T2. So with that, our equation would be simply equal to, since these are just slabs, so that is equal to A sub 1 multiplied with our thermal conductivity, and then the change in temperature divided by our delta x1. And instead of having instead of having something like a series conduction where we would add a resistance here, we will be adding the effects of the conduction to this material instead. By the way, it should be K1 and then K2. This one is also K2. So that is our final equation for two slabs. And this is a lot easier than in series, because you just have to add all the heat of conduction that is experienced by each material. So this material can also be something like, let's say we have a slab, and then the other one is like a hollow sphere. So in that case, if the heat flows through something like that, then these two materials will experience this kind of heat, and then your Qt is just Q1 plus Q2. And of course, Q1 will be for slab, something like this, and then Q2 is of course for the material that is sphere. Okay, and that's how it goes for parallel. So what if the problem would have something like a series and a parallel? Let's say there is a slab. Let's say there's something like that. Okay, let's make it something like 3D. That's a very distorted drawing, but So for example, this one is one slab which has a reinforced, they have three components for that. And then we do have something like this, another slab. Sorry, let's redraw it. So another slab with just two components. So if heat travels from this portion going to that portion, and this one's going to that portion, then in this case you would be using something like a series. If you would just consider this heat flow, and then this one would be also in series with just two resistances, and after that you would add for the total of this one, something like if we have here 1 and then 2, so QT is actually equal to Q1 plus Q2. That's because they are in parallel, but Q1 is also equal to the series combination of that R1 plus R2 plus, or let's just say A, B, and C. So that is the temperature gradient for 1, and Q2 is simply the temperature gradient at Q2, and then that is equal to, let's say, RA and RB. So that's how it goes for a series in parallel. So okay, so that's how it goes for our series and parallel conduction. Okay, I hope you've learned something from this, and these topics are really, these are not really difficult. It's just that you have to analyze the problem and understand where the heat flows, and if you've done that, then you're good to go. Okay, so thank you and see you next time.